page 114, section 2.6. 114, section 2.6. All right, for page 115, they ask us to find the slope of a tangent line to a curve at a particular point, and we also will find the equation of that tangent line to the curve at a particular point. So if you remember from geometry, the definition of a tangent line is typically a line that touches the graph or the circle or the curve, whatever it is you're working with, in exactly one point, right? So if I were to draw a tangent line, basically at a particular point, like if they say you've got the point A, f of A right here, draw a tangent line to that point, my goal would be to try and draw a line that only touched the graph at one point, and it was the precise point A, f of A. The problem with that is if I'm going to find the slope of that tangent line, or I'm going to find the equation of that tangent line, I need 2 points, right? Like I have to be able to do y2 minus y1 over x2 minus x1, or I have to be able to count my rise over run from one point to another. I need 2 points. And so I'm going to use a secant line. You might remember from geometry, a secant line is a line that would intersect your curve in 2 spots, right? So what I'm going to do is I'm going to go back and I'm going to draw a secant line that will intersect my graph in 2 points, one of them being that same point, A, f of A. And then we'll choose a second point, and I'm going to label that point x, f of x, okay? So if I were to find the slope of that line, I could use it as an approximation for the slope of my blue line. The only problem with that is that's going to be a terrible approximation, right? I mean, if I'm looking at the slope of my blue line, it looks like it might be maybe +1 or +2, something like that. Whereas the slope of this secant line looks like it's going to be closer to maybe 1/2 or 3/4. Not going to be a good approximation. So what would make the slope of that secant line a better approximation for the slope of my tangent line? Any suggestions? What would make the slope of the secant line a better approximation of the slope of the tangent line? All right, what if I drew my 2 points? We have to use that A, f of A, but what if I selected that other point instead of being over there? What if I selected it somewhere else? Where would make it a better approximation? If it was closer, yeah. So if I chose a second point, instead of being way over here, x, f of x, if I chose it to be over here, x, f of x, look how much of a better approximation that green line is to the blue line than the original red dotted one was, right? So if we went even closer, you can see that I kept my same A, f of A, but this time I chose x, f of x to be right there, even closer to my original point. And that orange line is an even better approximation to my blue line. So in essence, I want to keep going, making these 2 points closer and closer and closer and closer until, in essence, the distance between those 2 points is almost indistinguishable, right? Like if I do have to have 2 separate points, but if I could get those 2 points so that they were so close, they were right beside each other, the distance between them was so minuscule that it was almost indistinguishable, then the slope of the secant line would be almost a perfect approximation of the slope of the tangent line, right? So in essence, I want the distance between these 2 points to get smaller and smaller and smaller and smaller and smaller, like 0.1, 0.01, 0.001, right? Sounds an awful lot like limit, doesn't it? So we're going to define the slope of our tangent line at the point A, f of A in this way. We are going to describe it as the limit as x approaches A of the slope of the secant line. All right, let's look at that. If we're talking about slope, we're literally talking about y2 minus y1 over x2 minus x1, right? So let's go back to our 2 points. We had the 2 points, A, f of A, and x, f of x. So if I did y2 minus y1, that'd be f of x minus f of a, over x2 minus x1, that'd be x minus a. You also could think of it as rise over run. If you look at the difference between the two y values, that's f of x minus f of a, that's my rise. And if you look at the difference between your two x values, that's my run, that's x minus a. You could think of it that way as well. So this would give me the slope of my secant line. But we said what gave us the really great approximation was when the distance between x and a was approaching 0, right? So the way that I can write that is I can say, okay, I want x to approach a. I want this point right here, x, to get closer and closer and closer and closer to a until they're almost indistinguishable. So the slope of my tangent line then could be defined as the slope of my secant line when I'm taking the limit as x is getting closer and closer and closer to a until there's almost an indistinguishable difference between them. All right, so let's look at an example. Example number 1, it says find the equation of the tangent line to the parabola y equals x squared at the point 1, 1. All right, so they gave me a point. If I'm going to create the equation of a line, I need a slope, right? So I'm going to go through and say, okay, from what we just set up here, the slope of the tangent line can be defined as the limit as x approaches a of f of x minus f of a divided by x minus a. All right, so let's go through and say limit as x approaches a. Well, my ordered pair is a f of a, so in our case, a is going to be 1. And our function, f of x, is x squared, so when we come right here and we say f of x, that's just going to be x squared minus f of a. Well, f of a comes from plugging your a value into your function. So 1 squared would just give me 1. That's the same thing as my y value, right? So f of a is just my y value. So when they say subtract f of a, I can just subtract that y value right there. And then I'm going to divide that by x minus a. And again, remember a was 1, so we'll divide that by x minus 1. So now we're back to doing limits, right? That's not well behaved, so if it's not well behaved, what can I do? Make it well behaved. How could I do that in this case? Alright, so we'll factor it as a difference of squares and cancel. And then what I'm left with is a polynomial, and that's well behaved, right? I can do direct substitution, and I'll get my limit as 2, and we're being real careful with that limit notation there as well, where we continue to write limit as x approaches 1 until I actually plug in 1 for x. Alright, so now I have a point and a slope, and I could create the equation of my line. So I'm going to use point slope form, slope intercept form, standard form, whichever you prefer. They didn't necessarily specify here, but we could give whatever version they want. So I'm going to use point slope form, which is y minus y1 is equal to m times x minus x1. And distribute my 2, so 2x minus 2, and add that 1 to the other side, so there it would be in slope intercept form if they'd rather that. Or move it all over to one side, set equal to 0 with no fractions if they prefer standard form. So that's one way that I can define the slope of my tangent line. Another way that I could define the slope of that tangent line, that was definition number 1 on page 115. They also give me a second definition over on page 117 for the slope of the tangent line. And here's where it comes from. The only difference in the two definitions is just in the way that I draw the graph. Like over here we had a f of a and x f of x as the 2 points that we used to find the slope of the secant line. On the second definition, they're going to redefine that as a f of a and a plus h f of a plus h. Here's their thought. Typically when we have a value subtracted from x, it's a horizontal shift and we represent it with an h, right? So that would be very natural for us to represent it in that way. If I said, if this is a and I want to move horizontally, then I'm going to say that distance that I move horizontally is just h. So if I start at a and I move over h, then I would be at a plus h for my second x value. So if a plus h is my x value, then f of a plus h would be my y value. So all they've done is they've left this first point a f of a, but they've renamed this second point a plus h, f of a plus h. So if I were to go through and find the slope of the secant line, I again would do y2 minus y1, f of a plus h minus f of a, over x2 minus x1, a plus h minus a. So if I had a plus h minus a, that would just leave me with h. And in that case, if I want the distance between these 2 points to be getting smaller and smaller, the distance between those 2 points is h. So I want h to be getting smaller and smaller and smaller. I want h then to be approaching 0. So I could say then that another definition of the slope of my tangent line at the point a f of a would be the slope of that secant line, y2 minus y1 over x2 minus x1, that we created right up here. And then I would say the limit as h approaches 0, because h is the distance between those 2 points, and I want that distance to get smaller and smaller until it's almost indistinguishable, like 0.1, 0.01, 0.001. Now, that should look remarkably familiar to us because that is our difference quotient, right? We started doing that last year in pre-calculus in chapter 1, and we did it 4 or 5 times last year, and we've already seen it again this year. So we already know how to do this part of it, that difference quotient part. And so that's why it's a fantastic way for us to define those 2 points, because we're already very familiar with that type of simplification. All right, so look at example 2. Example number 2 asks me to do the exact same thing. Find the equation of the tangent line to the graph y is equal to 3 over x at the point 3, 1, only this time we're going to use that second definition instead of the first. All right, so we'll go through, and they've told me f of x is 3 over x, and they've told me my point is 3, 1. If I'm creating the equation of a line, I have a point, I need a slope. So I'm going to use that definition of slope that we just created right here. So I could go through and I could say, all right, if a is equal to 3, then let's put a in the place, 3 in the place of a, so that would be f of 3 plus h. And let's put 3 in the place of a, so that would be f of 3. And then we're going to divide that whole thing by h. All right, so f of 3 plus h literally means put 3 plus h in the place of x in that function, right? F of 3 plus h literally means put 3 plus h in the place of x in that function. So that's going to give me 3 over 3 plus h. I'm putting 3 plus h in the place of x in that function. Right? Then I'm going to subtract f of 3. Now remember, f of 3 is just what I get when I put 3 in the place of x, so that'd be 3 over 3. It's also the same thing as my y value, so I could just automatically put 1 in there as well. And divided by h. All right, we don't like to have fractions inside of fractions. We call those complex fractions. And so remember, the way that you can get rid of fractions inside of fractions is you can multiply by the least common denominator to clear all of your fractions. So I have 3 plus h and 3. So if I multiply top and bottom by 3 plus h times 3, then that'll clear out all of my fractions. So if we go through and do that for this first piece, if I have 3 over 3 plus h and I multiply it, the 3 plus h is going to cancel, and that would leave me with just 3 times 3. So that would be 9. And then for the second one here, the 3's are going to cancel, and that would leave me with 3 times 3 plus h. And in my denominator, of course, nothing cancels, so I still have everything. I have the 3, the h, and the 3 plus h. And then we can do some simplifying, because as this stands right now, that limit is not well behaved. So let's do some simplifying. I'm going to distribute this negative 3 up here in the numerator. So negative 3 times 3 would give me negative 9, and negative 3 times h would give me negative 3h. My 9 minus 9 would drop out, leaving me with just negative 3h in the top. and then I could cancel that 3h top and bottom, leaving me with a rational function that is well behaved because 0 is within its domain. So again, we've simplified those difference quotients before, so we're very familiar with those. And we've done that algebraic simplification with limits in the last couple of sections, so we're comfortable with that. So we're just kind of putting those two ideas together. So now I have a point and I have a slope, so I could create the equation of my line. And again, I could use point slope form, I could use standard form, I could use slope intercept form, you know, whatever we want there. So I'm going to do y minus y1 is equal to m times x minus x1. If they want me to switch it to one of those other forms, I will. All right, look at example 3. Example number 3 says, find the slopes of the tangent lines to the graphs of the function f of x is equal to the square root of x at the points 1, 1, 4, 2, and 9, 3. You're kidding me. You want me to do like what I just did right there to get 1 point? You want me to do that 3 different times to find the slope at 3 different points? Like one problem is going to take me forever. All right, well, let me make a suggestion to you. If they ask you to find the slope at just 1 point, then yes, we're going to go ahead and we're going to plug in the a value from the very beginning and find the slope at just that 1 point. However, if they ask me to do, like in example 3, if they ask me to find the slope at multiple points, instead of plugging in 1 for a, or plugging in 4 for a, or plugging in 9 for a, just find the slope at a. Let me show you what I'm talking about. I'm going to find the slope at a. All right, so I'm going to go through, my function was f of x is equal to the square root of x. So I'm going to use our definition of a limit, which is the limit as h approaches 0 of f of a plus h minus f of a divided by h. So f of a plus h literally means put a plus h in the place of x in that function, right? So let's put a plus a h in the place of x in that function. So we'd have the square root of a plus h. Then we're going to subtract from that f of a. So that just says put a in the place of x in that function. Put a in the place of x in that function. So that would give me square root of a. And then divide the whole thing by h. Of course, my limit is not well behaved. So I have to do some kind of crazy algebra to make it well behaved. So what did we do when we had radicals? Yep. Multiplied by the conjugate, right. You could call it rationalizing your numerator just like we would normally rationalize a denominator, or you could call it multiplying by a conjugate. All right. So I'm going to go through and I'm going to multiply by the exact same thing that I had here, square root of a plus h and square root of a. But instead of the subtraction sign, we're going to use the addition sign. That's how we get the conjugate, right? Everything else stays the same. We only change the sign in between the two terms. And of course, what I do to the numerator, I also have to do to the denominator. All right, so let's FOIL out that numerator. If we FOIL out that numerator, square root of a plus h times square root of a plus h would just give us a plus h. Square root of a plus h times a positive square root of a, and square root of a plus h times a negative square root of a would cancel each other out. And then negative square root of a times positive square root of a would give us a negative a. So all we did was FOIL there. In my denominator, I'm just going to bring everything along. I'm not even going to bother to distribute that h because our goal is to get it to cancel anyway. All right, so then in our numerator, the a and the negative a will drop each other out, leaving me with just h in the numerator. And then I can cancel the h in my numerator with the h in my denominator, right? So then what I'm left with is something that I can check and hopefully see that it's well behaved. Let's try it and see. So if we go through and we put 0 in the place of h right there, that would give us the square root of a plus 0. Yeah, I'm good. That'd be the square root of a plus the square root of a, so that would just be 2 square roots of a. So here's what I just created. I just created a formula to find the slope at any a value they want to give me. Because I did not from the very beginning plug 1 in for a, or plug 4 in for a, or plug 9 in for a, I didn't get a number like I did last time. That would have been the slope at just that point. But what I now have is a formula that I could use to find the slope at multiple points. So watch this. I can go through and say, okay, if my slope is 1 over 2 square roots of a, if that's the formula for this slope, and I want to know the slope at 1, 1, remember that 1, 1, that's a f of a, or that's my a value, my y value. You could think of it that way. So all I'm going to do is put 1 in the place of a. So if I put 1 in the place of a, there's my slope. So if I wanted to know the slope at 4, 2, again, this is my formula that we just created for slope. So at 4, 2, what is a? Which of those is my a value, 4 or 2? 4, So I could take 4 and put it in the place of a. So if I put 4 in the place of a, I'll get 1/4. Then I could do the point 9, 3. At 9, 3, which of those is my a value, 9 or 3? 9, right. So I could throw the 9 in, and I've got my slope. So if they ask me to evaluate the slope at just one point, I absolutely am going to plug the number in from the very beginning like we did in examples 1 and 2, because I'd much rather work with numbers than letters. It's just easier. It simplifies faster. But if they ask me to find the slope at multiple points, unless you want to go back and you want to do all of that work 3 times over to get the 3 different slopes, what you can do is, instead of plugging in a number for a, just leave a in there. And instead of getting a number at the end, you will get an equation at the end that you could plug multiple a values into to find multiple slopes. So those would be our 3 different slopes, and if they wanted me to create equations of lines to go with them, I would then have a point and slope, and I could do that. All right, so this is our homework for tonight. We obviously are not doing 15 of these. 4 will be plenty. So we're doing page 122, 5, 7, 9, and 11. 5, 7, 9, and 11. On some of the homework problems, they'll say do this by definition number 1 or do this by definition number 2. Remember that we defined our slope in 2 different ways. Example number 1, we use definition number 1. Example number 2, we use definition number 2. So that's what they're talking about there.